So here's the third and final example that I'm going to do for you guys for one-dimensional kinematics. Just like the previous two videos, I would strongly encourage you guys to take a moment and try and solve as much of this problem as possible without my assistance, just so that you start to lean off of that crutch a little bit, because you will eventually have to do this on your own. So go ahead and take a second now to pause the video and see what you can get done without me. So just like the other problems we did previously, I'm going to go ahead and draw a picture so I understand what's going on here. We've got Doc Ock outside, got to give him a head, and he takes his Octobot and he throws it up, and he says he throws it straight up into the air. So technically it should go up and come straight back down, but just so that we can see the path a little better, I'm going to push it off to the side just a little bit. So it's going to go all the way up, eventually stop, turn around, and come back down to the ground. So he falls back to the ground. What I see here are two specific moments that we care about. We care about the moment it leaves his hand, so we'll call that position 0. And then we care about when it hits the ground. We'll call that position 1. So the way this goes is it's going to go up, pass back down, and hit the ground. So we've got a position 0, we've got a velocity 0, we've got a time between 0 and 1, and since these are the only time periods, I'm going to cheat a little bit and just call that time. Instead of saying t 0 to 1, let's just call it time. With the acceleration, again we're going from 0 to 1, but this is the only acceleration, so we're going to cheat a little bit and call it a as well. So after we pass through those, we go to position 1 with velocity 1. So at this point, I'm going to go ahead and decide where my 0 position is. Most of you guys, it seems, are more comfortable starting your initial position at 0. And I said go ahead and do that, and we did a practice problem like that. The first example, we just went ahead and said that that was going to be 0. But we discovered that when we did that, then our final position ended up being negative. So I'm going to modify this a little bit, and I'm going to say that the ground is our 0 position this time. And that makes sense, because very, very few things will go lower than a ground. Unless we end up hitting a hole or something like that, the ground tends to be your 0 position. So that means any other position that we have is going to have to be positive. Speaking of which, let's go ahead and define that now. We're going to say up is positive and down is negative. So that means x0, where we start, is we're starting 1.5 meters above the ground. This is going to be positive 1.5. He is currently throwing it with up, so positive 12 meters per second. The time is our end goal here. We need to figure out how long it's in the air for. The acceleration. Well, since this object is technically in free fall, the acceleration is going to be negative because it's pulling it down, 9.8 meters per second. That's the acceleration due to gravity. And some people might argue at this point and say, but hold on, Mr. Raymond, it's not in free fall. It's going up, and then it's in free fall. But free fall is defined as anything that is just being acted on by the Earth. So only if Earth's gravitational, or if you're on some other planet, only the planet's gravitational pull is acting on the object. If this was a human being or a rocket that was going up and then coming back down, or if a human being was holding the Octobot, moving it up and bringing it back down, or if a rocket was bringing it up and bringing it back down, then it wouldn't always be in free fall. But since nothing is physically touching this Octobot after it leaves his hand, then we can consider it in free fall. So now that we've got a bunch of stuff plugged in, we need to figure out what we want and what we have. Well, ultimately, what we want is we want the time. And what we have is we have the initial position, we have the initial velocity, we've got the acceleration, and we've got the final position. And again, I'm going to pause. I'm going to say there's actually multiple ways to do this problem. I'm going to show you two slightly different ways. One of them, some people are going to find easier if you have a calculator or if you're good at factoring. The other is going to be pure algebra, but you end up having to do 2 steps. So the first thing I'm going to show you is people who are good with their calculator or good with factoring, or if you have some kind of technology, this is going to be the best way for you. So I've found a majority of people will do this the graphing method. If you decide to use this method, you're going to graph. Most people aren't going to factor it. And the equation that will actually give us what we want is this one right here. x1 is equal to x naught plus v naught t. Oh, sorry, v naught, the t is a variable, it's not part of a subscript, plus 1/2 at squared. So we're going to go ahead and plug in our zeros, which leaves us 0 is equal to x naught plus v naught t plus 1/2 at squared. And at this point, some of you are thinking, well, hold up a second. You're getting a little idea of what's going wrong here. If you try and rearrange this equation to get t by itself, you're going to have to factor. So you're either going to have to complete the square, or you're going to have to use quadratic equation, or you're going to have to get creative with how you factor this. I'm not a huge fan of doing that factoring, plus I've got a calculator right next to me. So if you know how to find the zeros of a function, what I want you to do is take your calculator and plug in 1.5, because that's our initial position, plus 12, that's our velocity, and then t. But in your calculator, when you're graphing it, don't put t, hit that variable button for me. So it's going to be that x, t, theta, n button that's on there. Or it looks like those letters for your variables. Plus 1/2. Don't forget that it's negative 9.8. And again, instead of hitting that t button, make sure you use that variable button. So now when you graph it, you can actually calculate those zeros. So you would hit, on a TI calculator, you would hit second calculate, and you'd hit those 0 buttons. And if you're not sure how to do it, then go ahead and ask a teacher or ask a fellow classmate, and they might be able to help you out. But you'll find out that you get 2 time points. You'll get the first one, the far left, is negative 0.119 seconds, and the other time point is 2.568 seconds. So we can't have 2 times that it's in the air for. And if you think about it, one of these answers just doesn't make sense. We can completely ignore the negative time. How can the Octobot be in the air for negative 0.119 seconds? And the answer is it can't. What that's doing is this is the mathematical representation of the thing that's happening. So we as intelligent students have to decide which of these answers make sense. Can it be both? Can it be in the air for 2 different time periods? And the answer is no. So then which of the 2 makes more sense? The positive number. So that again is using through graphing method. If you don't have a graphing calculator, or if you don't want to do any sort of factoring method, then what you're going to end up having to do is a 2-step problem. Since we can't solve straight for time, we should solve for v1 first. So I'm going to go ahead and look through all these equations here, and I discover that v1 squared is equal to v naught squared plus 2a x1 minus x naught. Again, plug in your zeros, and you'll get 0 there, leaving you with the equation v1 squared equals v naught squared plus 2a negative x naught. Don't forget that that negative still exists. Now we ultimately need to get v1 by itself, so we take the square root of both sides. And here's where people make a mistake. You go through and you plug into your calculator and you get a number, and it turns out your calculator lies to you. So when you go to plug into your calculator, v naught squared, well, v naught is 12 plus 2 times negative 9.8 times negative 1.5. When you plug in your calculator, it gives you that v1 is equal to 13.168. And here's the issue. Again, we as intelligent students should recognize immediately that this is a mistake. This is saying that when you hit the ground, you're moving up with a velocity of 13.168 meters per second, which doesn't make any sense. So how do we make it say down? Well, the error was right here. We trusted our calculator too much. Anytime you take the square root of something, you end up with plus or minus. So this answer here is plus or minus 13.168. So again, we as intelligent students have to decide, is the answer positive 13 or negative 13? Well, since our object is moving down, we should have a negative velocity. So we have to use a little bit of thinking more so in this one than we would for the graphing method. So now that we have V1, we can use V1, which again makes me a little bit uncomfortable. I'd rather not use answers that I solved for in my equation. But again, that's just me personally. I'm always skeptical just in case I made a little mistake. So I'm rearranging to get my variable by itself. So now we'll go ahead and divide by A. And we'll get that V1 minus V0 over A equals T. Plug in those known values. Our V1 is negative 13.168 minus 12 divided by negative 9.8 gives us that T value of 2.568. So in both cases, we get the same answer. So our final answer, how long is it in the air for? It is in the air for 2.568 seconds.